A very good afternoon to all of you. So let us begin today's session. This is session number 12, and in today's session we are going to see the topic transmission line models. So as in the last two classes, last two sessions, we have seen the parameters of transmission line. We know that a transmission line is can be represented by using the four parameters: resistance, inductance, capacitance, conductance. All four parameters that are among all four parameters, we have to know how to calculate the inductance and capacitance. That is very much important. Now after knowing how to calculate this distributed inductance and capacitance, now we need to model this transmission line. So now we are going to model the transmission lines, and these are some of the important notations that you keep it in mind, like a small z that represents the series impedance per unit length, and a small y that represents shunt admittance per unit length, and capital Z that is total series impedance, and it's multiplied by the series impedance per unit length with the its total length, and a capital Y represents the total shunt admittance, and a small l represents the line length in meter. So uh, to model the transmission line, we use the ABCD parameter. That is we all know that that is one of the type of two-port network. So we often interested in this terminal characteristics of transmission line only. So if this either sending or receiving in sides voltage currents are given, then we can find the other side voltage or current. Two parameters should be known so that you can find the other two parameters with this help of ABCD parameter. So in this session, we are going to see how can we can find the ABCD parameter for short transmission line, medium transmission line, and long transmission line. If we see this matrix, then we can say that this A and D are the dimensionless because this A is equal to Vs divided by Vr. Both sides are voltage, numerator and denominator both are voltages, so it is dimensionless. And similarly, D is also dimensionless because it is the ratio of sending in current to the receiving in current. And C represents the mho, that is opposite of ohm, and B represents the impedance, and that unit is ohm. Now we are going to see the transmission line model for these are the summary point. We use the two-port network for the transmission line modeling, and this is the equation you will get by this matrix by this ABCD parameter, and AD minus BC is equal to 1. This is the one of the important properties of ABCD parameter, and this as I shown in the first slide, small z and small y that you can represent y r plus j omega l series impedance per unit length, and a small y g plus j omega c shunt admittance per unit length, where g is the conductance and j omega c you can also say it as jb, and where b is the susceptance of the line per unit length, and a capital Z is the total series impedance, and capital Y is the total shunt admittance. Now for short transmission line, usually we take the length should be lesser than 80 kilometer. So that comes under short transmission line, and we model this transmission line accordingly. For short transmission line, we neglect this shunt admittance due to shorter length. So if we neglect this shunt admittance, then this is equal to IR, so C will be 0. So this is important. We neglect the shunt admittance because this line charging current is very small in shorter transmission line. So that's why Is is equal to IR. So C value is 0. And this Vs you can just use the KVL. Vs is equal to VR plus ZIR. Z is the total impedance of the line. So you will get the ABCD parameter here, and just you we know that this AD minus BC is equal to 1. This is coming, and A is equal to D is equal to 1, and B is impedance of the line Z ohm, and C value is 0 Siemens. Now coming to the medium length transmission line. So in shorter and medium length transmission line, we consider the lump parameters. So here we have also we can see that we have considered the lumped parameters, that we just collected this at one point, that is total impedance of the line. Similarly, in this medium transmission line, we also consider lumped parameter, but here shunt admittance is considered, and we take this shunt admittance at both the end of the line. So this is called as the pi nominal. This is called the pi modeling, nominal pi circuit. So half of the shunt capacitance can be considered to be lumped at each end of the line. So this is called nominal pi circuit. One other representation is nominal T circuit is also there, but we will see only this nominal pi circuit because this is much more important than nominal T circuit. So if you want to write this Vs equation, voltage equation, then you have to apply KVL here. Vs is equal to VR plus ZIR plus VR by 2. So upon rearranging this term, you will get 1 plus YZ divided by 2 VR plus ZIR volt, and Is you will get IR plus VR by 2 plus Vs by 2. Just looking on this figure carefully, you can get these values. If you face any doubt or any problem, then you can tell me. I think,
Can you can you explain with the help of figure how to remember these formulas, sir? VSIS.
okay,
Any short trick is there, sir, with the help of figure?
yeah, it is simple. You have to, for Vs, you have to apply the KVL. So
Okay. Okay.
we are applying KVL for VS. I am writing one, you can write another one. So VS will be, so taking from this side, uh, left hand side, so Vs will be equal to VR plus this this will come as, because this point is VR, right?
Yes, sir. Yes, sir.
So you have to just write the voltage across this Z. So voltage across Z will be VR plus VZ. So current, how much current flowing through this? IR current flowing through this, and this current is this current.
IC. IC by 2.
So VR into by 2. Correct. This will you current through this capacitance. Are you getting this?
Getting, sir.
Okay. So IR plus VR by 2 in the current flowing through this impedance. So we can write that here current is IR plus VR by 2
To
and
Z.
Z. Correct. So this is very simple. You write the first make the model and represent VS, IS, VR, IR, and you represent this by 2 Z. That's all. And you just apply KVL and KCL. You will get this form. And in writing down in ABCD parameter, you have to You have to express this in terms of VR and IR. So you will get these terms. So here we can see that A is equal to D, and this is 1 plus YZ by 2, and B is the impedance of line, that is Z ohm, and C is the mho, and that is Y 1 plus YZ divided by 4, or its unit is Siemens. And medium length transmission line, how much length this is? 80 to 250 kilometer. Usually we take the length as 80 to 250 kilometer. Now one important terms come here is that voltage regulation.
Sir, I have one doubt, sir.
Yes,
Transmission lines are classified based on which criteria, sir?
transmission line.
Transmission lines are classified based on which criteria?
Transmission line is characterized based on this length of the transmission line. But in some textbook, you can also find that they can classified in the terms of frequency into length. So if we increase the frequency, then it is for the 50 hertz line. We are in India. We are using 50 hertz line. So frequency is 50 hertz. Accordingly, I have taken this length of transmission line. But if frequency is changing, this length will get changed, right? Are you able to understand or not? Hello, are you there? Who asked this question?
Hello, sir.
Yes.
If this formula will change with frequency, then how we can tackle with this problem?
No, no, formula will not change. For medium length transmission line, this is specified there that you have to use the nominal pi circuit. So formula will not change. But he was asking that how we classify this short length, medium length, and long length transmission line. So I was telling that thing.
Okay, sir. Okay.
Yeah, for short length transmission line, we usually take the length should be less than 80 kilometer. But this ABCD parameter will remain same. It will not change. And for medium length transmission line, we use the nominal pi modeling. Now the coming to this voltage regulation. So voltage regulation is the change in voltage at the receiving end of line when load varies from the no load to a specified full load at a specified power factor when sending in voltage is held constant. So nominal voltage expression is that how much your receiving end voltage varies from the no load to full load. So it is the ratio of ratio of difference in no load and full load receiving voltage divided by the full load receiving voltage. So this is important. And generally we have to this consider this according to like voltage deviation at the bus should not be more than it should be a tolerance value plus minus 5% of the rated voltage that we generally take it as. And if you see this lagging power factor load, then current is lagging herein. So this is the phasor diagram for lagging power factor load, and similarly we can find this phasor diagram for leading power factor load.
Yes, sir. Sir, I think in India it is 6% tolerance.
It depends on the standards. There are different standards. So depending upon the standards, which standards are you referring? So like generally this voltage should be plus minus 5 uh, percent of the rated voltage, and lower and below it should not deviate more than that. Like there are different standards, IEEE standards, IEC standards. So whatever the standards you see, there you have to uh, consider that. Now, based
Oh,
on this modeling and voltage regulation, we will solve one problem. So here this first problem is that a three-phase 60 Hz completely transposed 345 kV 200 kilometer line has the following line constraints, where Z is given as 0.032 plus J 0.35 ohm per kilometer and Y is plus J 4.2 into 10 to the power minus 6 Siemens per kilometer. Full load at the receiving end of the line is 700 megawatt at 0.995 power factor leading and at 95% of rated voltage. Assuming a medium length line, determine the flowing ABCD parameters of the nominal pi circuit. So we are going to see this nominal pi circuit modeling, and it is given as medium length line. So we know that for medium length transmission line, how you are going to write this ABCD parameter. 1 plus yz divided by 2, b is z, and c is y into 1 plus yz divided by 4, and d is equal to a 1 plus yz divided by 2. VR IR. Now we will first find this total admittance or total impedance of the line. So total admittance will be pi into L. Y is given as J 4.2 cross 10 to the power minus 6 and length is 200 kilometer. So it is coming as J 840 cross 10 to the power minus 6 Siemens. Whoever is getting the answer, you can type it on the chat box. A, B, C, D, whatever value you are getting, you can type it on the chat box. ZL is 0.032 plus J 0.35 cross multiplied by 200 ohm. So it will be 6.4 plus J 70 ohm. Now we are going to find these two parameters. A is equal to D. So this is 1 plus YZ divided by 2, 1 plus 6.4 plus J70 cross J840 into 10 to the power minus 6 divided by 2. So you will get 0.97 plus J 2.688 Siemens. So it is 0.9706.159 degree. It is unitless, so no need to write the unit. Now we will find this B and C parameters. So B parameter is simply the impedance of line. So impedance we have calculated 6.4 plus J70 ohm, writing it in phasor form 70.29 84.78 degree ohm. Similarly, we can find this C value. C value is pi into 1 plus yz divided by 4. C is J 840 into 10 to the power minus 6 1 plus 6.4 plus J70 into J840 10 to the power minus 6 divided by 4. So C will come as minus 1.18 into 10 to the power minus 6 plus J 8.27 into 10 to the power minus 4. So C value is 8.27 into 10 to the power minus 4, 90.08 degree ohm. No, so its unit is mho or Siemens. So first part we have calculated, that is ABCD parameter nominal pi circuit. Now we are going to calculate the B part, that is the sending in voltage, current and real power PS. So we will use this expression Vs is equal to AVR plus BIR. Can anyone tell this Vs and VR in phase or line to line voltage?
Phase voltage, sir.
Yes,
Phase voltages.
yes, correct. So we have to take this phase voltage. That is very important. So in the problem, you can see that it is given that receiving in voltage is 95% of the rated voltage. So first we will find this receiving in voltage so that we can find the sending in voltage. So take it as reference. So VR will be 0.95 into 345 divided by root 3 at the angle of 0 degree kV. It will be 189.226 at the angle of 0 kV. So now we also need to find IR to find VS. So IR, how we can find? We will find using this power, because power is given here. Power is given 700 megawatt at 0.955 leading. So using power factor, using power expression, active power expression, we know that 3 VR IR cos phi. We have used this expression because this we are taking the phase value of voltage. So from here we will get the IR value, magnitude of IR. So PR is given as 700 megawatt, 3 into, and VR magnitude is given as 189.226. IR is given and cos phi is given as 0.99. IR we have to find, sorry, IR magnitude will be come as 1.2455 kilo ampere. Why I am writing kilo ampere? Because this is in power in megawatt and this voltage in kilovolt. So current will come in kilo ampere. So directly keep in mind this, it is not in ampere. And if you want to write this in phasor value, then this will be 1.2455 cos inverse cos phi is given as 0.99, then phi will become as 8.11 degree. So since it is leading, so 8.11 plus 8.11 degree. So IR comes here. Now we will apply this in first expression. Vs is equal to AVR plus BIR. So, so then Vs will be A value is 0.9706.159 degree, and VR magnitude is VR value is 189.226. It is at the angle of 0 degrees, so I am writing only magnitude. We have taken it as reference. So 70.29 84.78 degree is B value, and IR value is 1.2455 at the angle of 8.11 degree. So we will get VS value as 199.66 26.134 kV. So similarly we will find this IS value. IS is CVR plus DIR. So IS value come as 8.277 into 10 to the power minus 4 at the angle of 90.08 degree. VR is 189.226 plus D value is 0.97 at the angle of 0.159 degree at the angle of 1.2455 8.1 degree. So IS will come as 1.241 at the angle of 15.44 kilo ampere. Now we can find the sending end voltage. So PS will be 3 Vs Is cos theta. Theta is the angle between the sending end voltage and sending end current. So how we can find theta? Theta is equal to, what is the difference between sending end voltage and sending end current? 26.134 degree minus 15.44 degree. So it is coming at 10.694 degree. So PS will be 3 into Vs is coming as 199.66. Is 1.244241 and cos of 10.694. So PS is coming as 730.4 megawatt, because voltage and current both are in kilovolt and kiloampere. And the next part is we have to find the percentage voltage regulation. C part is, here we have to find the percentage voltage regulation. So we know that percentage voltage regulation is no load receiving voltage minus full load receiving voltage and full load receiving voltage. What will be the no load receiving voltage? Can anyone tell? Because we know that full load receiving voltage is how much? Sorry. Full load receiving voltage is given. We have found out this. That is 95% of rated value. So it is coming as 189.226 kilovolt. So what is the no load voltage? Can anyone know this?
Yes, sir.
What is the
One,
no load?
199.185.
How we have calculated?
Phase voltage, sir. 345 by root 3.
That is actually incorrect. So so we have to find this no load receiving voltage. So we will use the again the ABCD parameter. So it will be not 345 divided by root 3. It is incorrect.
Okay.
How we are going to find this? We know that Vs is equal to AVR plus BIR. So at no load means IR is equal to 0. So Vs no load is equal to A into
Yeah. Yeah.
VR no load. So Vs no load divided by A. So Vs no load, we have found this value. What is this value? 199.6. You can directly write Vs by A because that is sending is voltage. So it's better to write VR no load is 199.6 and A value is 0.9706. So it is coming at 205 point.
205.219.
What is the value?
205.219.
Yeah, that is approximately coming this one. So now we are finally putting all these values. Percentage voltage regulation is 205.64665. You can 65 minus 109.266 divided by 266 into 100. So it is coming as 8.67%. So this is the percentage voltage regulation. Now
Yes,
last
sir.
last part is,
8.67.
yeah, correct. Very good. So now we are going to see transmission line efficiency. Transmission line efficiency will be P out divided by P in, P out divided by P in into 100%. So P out will be what? That is PR and sending it PS into 100%. So we have found this PR is given in the problem, that is 700 megawatt, and PS, uh, yes, 700 megawatt, and we have found this PS. We have found this PS as 730.4 megawatt. So put these values, 700 divided by 730.4 into 100. So it is 95.84%.
95.3.
Correct. So this is very important question from this nominal pi circuit that is used for modeling of medium length transmission line. And if you solve this problem, I think you are able to solve all type of problem related to this one. Now we are coming to long transmission line. So what we have considered? We have considered that in short and medium length transmission line, the parameters are lumped. That we have consider that resistance inductance are at lumped. They are not distributed throughout the line. And in short transmission line, we have neglected the admittance of line. And while we have in medium transmission line, we have considered the admittance of line as at each end of the line, which is half of the total value. Now for long transmission line, we are we are considering this as distributed flow for long length line for whole the distance. So for deriving this modeling of transmission line, we will use this like we will use this delta x distance. How much if we vary the distance delta x over the length of transmission line, what will be the difference in this voltage and current? So we can write this KVL equation here. Vx plus delta x is equal to Z delta x plus Vx. Now taking this value Vx plus delta x and Vx this side divided by delta x is equal to Zix. So since delta x is tending to 0 because we have considered a very infinitesimal a small distance. So this is the expression for the derivative term. So you can write dvx divided by dx Zix. So we have taken it. We can consider this as first equation. Now similarly we can write the KCL in this long length transmission line. Ix plus delta x is equal to y delta x Vx plus delta x plus Ix. Now again take this term Ix to the left hand side and divide by delta x, you will get this expression. And since this distance is very small, so this is the expression for derivative term. So you can write this as equation 2. Now differentiate this first equation and substitute this equation number 2. So you will get this term. Now we will take some assumption. We can take this zy as the gamma square, where gamma is the propagation constant. This is important. Gamma square is equal to zy, a small zy, and we know that solution for this differential equation will be Vx is equal to C1 e gamma x plus C2 e to the power minus gamma x. So this is the solution for this equation. Now we have we can write down that where gamma is the alpha plus j beta, that is the under root of zy, and where alpha is the attenuation constant and beta is the phase constant, and beta is written in the radian per unit length. So again we are going to this first expression. First expression we have seen that dvx divided dx Zix. So we are going to substitute this term Vx term. We are going to substitute Vx term in the first one. So this is the first term. So we got the solution. So we can put this Vx value here. So upon taking the derivative of Vx, you will get this gamma outside, and here you will come minus term will come, and z will come this side. So you will get Ix in terms of, so you will get Vx and Ix in term of propagation constant. So similarly here we can represent Ix in the terms of characteristic impedance, and characteristic impedance is the a square root of reciprocal of per unit impedance divided by the per unit admittance. So now we use the sub conditions that when this distance is 0, then Vx is Vr. So we are considering from the receiving end side. So this Vx is equal to Vr and Ix is equal to Ir, so that we can get C1 and C2. So when you consider this Vx x is equal to 0, then substitute this value here, this Vr. So you will get Vr is equal to C1 plus C2, and similarly substitute in Ix is equal to Ir in the current expression. then you will get 1 divided by ZC. Here you can see 1 divided by ZC. This x will be 0, then C1 minus C2. Upon solving this term, you will get the C1 and C2 expression, right? So now we got this. Now this C1 and C2 we got. So again we put this C1 and C2 in third and fourth expression here. So we will get this expression Vx, and that is important. And up, rearranging these terms in Vr and Ir on the for writing in ABCD parameter. So we will get like this, and we know that this term is E gamma x plus E gamma minus x divided 2 is cos h gamma x. And similarly, this if minus comes, then it is sine hyperbolic function. So cos hyperbolic function and sine hyperbolic function. So we will get this expression. So we have finally found this Vx Ix in the terms of, like rearranging terms of Vr receiving in voltage and receiving in current. So our interest is in the relation between sending and receiving in the line. So that is important. So what we will do, we will put the whole distance x is equal to L. Then VL will be Vs and IL will be Is. On substituting this x is equal to L and this expression, you will get the Vs Is term here, and finally you will get the ABCD parameter for long length transmission line. Any doubt in understanding this derivation? Amandeep, you have doubt?
Sir, after the lecture, can you please share these PPTs with us on the email?
I'm sharing this PPT on my YouTube channel, so here we can get that.
Okay, okay. So, can we get the YouTube channel link in the chat box?
Yeah, you can simply. I've shared once. I'm uploading the video there also for more
Okay, okay.
Okay, all right. So this is
Thank you, sir.
very easy, not that much difficult. Just
Yes, sir.
just you have to uh, write down this first KCL and KVL expression and just remember the step.
Yes, sir.
And derivation is not very important, but I am uh, telling you so that you can gain confidence. So finally we got this ABCD parameter for long length transmission line, and so this you need to keep in mind. Now we are going to, so this is the uh, hyperbolic cos hyperbolic function and sine hyperbolic function I have written down for your reference. So if you take the derivatives, there is no negative terms come here, both will be positive. Cos term will come convert into sine and sine term will convert into cos, that we have used in the derivation. So I have written down here. Now if you want to write in equivalent pi circuit model, so we know that pi circuit model, how we are going to represent. We have taken the total impedance of line in the center and admittance at half at the both end of the line. So first you write this expression that we know that from pi circuit modeling. So upon writing this expression for pi circuit modeling, you just represent by dash by 2 and just equate this expression with the previous one that we got cos h gamma l sin h gamma zc sin h gamma l. On on equating this term with previous one, you will get this z dash and y dash 2. So you will get this z dash and y dash by 2. So here z dash will be Z sine H gamma L divided by gamma L, and by dash by 2 is by divided by 2 tan H gamma L divided by 2 gamma L divided by 2. So this expression you can represent the long transmission line in the pi equivalent circuit also. So this is also important. So is there any doubt till here?
No, sir.
You can get this expression upon substituting characteristic impedance. This similar expression. Just revise after the class. Just do the homework like thing. Now we are going to solve one problem on long transmission line. Here a long transmission line delivers a load of 60 MVA at 124 kV 50 Hz at 0.8 power factor lagging. Resistance of the line is 25.3 ohm. Reactance is 66.5 ohm. Admittance due to charging capacitance is 0.442 into 10 to the power minus 3 mho. Determine the following ABCD parameters. So many things are given. First we write down what are the things are given. This total resistance of line is given as 25.3 ohm and reactance is 66.5 ohm, and so Z will be 25.3 plus 66.5 ohm, and then Y is J 0.442 into 10 to the power minus 3 mho. Then for finding ABCD parameters we have to find this gamma L first, because if we see the ABCD in the long transmission line, then A is coming as cos H gamma L, B is coming as ZC sin H gamma L, C is coming as 1 divided by ZC sin H gamma L, and cos H gamma L. If you are like writing this ABCD parameter, suppose you have written wrong, then you can verify using this statement: A is equal to D and AD is equal to minus AD minus BC is equal to 1. These criteria should satisfy. So if this is satisfying, then you have written these ABCD parameters correctly. So keep it in mind. So cos in hyperbolic function cos square minus sin square is equal to 1. So that will also satisfy this. So let us first find this gamma L, then only we can find the ABCD parameters. Gamma L is a small z by into L. So take this small uh, L inside, so that it will be converted into the total values z into y. Then we are given with z and y. So z will be 65.3 plus 66.5, y is j.442 into 10 to the power minus 3. So on solving this, you will get gamma L as a 0.0327 plus J 0.174. Therefore, we can write A is equal to D is equal to cos H gamma L, that is cos H root of ZY. So gamma L is nothing but total impedance and total admittance, a square root of total admittance and total impedance. So hyperbolic cos 0.03217 plus j 0.174, you will get 0.986, 0.32, and you will get B value ZC sin H gamma L. So characteristic impedance, we have seen that a small z divided by we have seen where here a small z divided by a square root of a small z divided by small y, impedance divided by admittance. So substitute both side, we can multiply with L, sorry, both numerator and denominator. So it will be capital Z divided by capital Y. So we will get this, sorry, what time. So we will get this one 393 point minus J 70.2.3. So put ZC here. So you will get B value as 70.3, 69.2 degree. Similarly, we know that C value 1 divided by ZC characteristic impedance sine hyperbolic gamma L. So it is reciprocal opposite of ZC by divided by Z sine of H root of ZY. So it will be coming as 4.44 cross 10 point minus 4 minus 90 degree. So it is J 4.44 into 10 to the power minus 4. So we have found this all ABCD parameter. Now we need to find the sending in voltage, current and power factor. So it is given that load is at 60 MVA. Load is at 60 MVA at 124 kV. So whatever the voltage we are given in the question, we have to consider that line to line. Therefore, load current will be IR will be 60 into, that is in MVA, so keep it in MVA, 60 divided by root 3 into 124. So it will be coming as 279.36 kilo ampere. This is magnitude, correct? Now we will find this total phasor form. So phasor form will be, since power factor is 0.8 lagging, so cos inverse of 0.8, that is comes here. So phasor form of IR is equal to 279.36 minus 36.87, sorry, it will be ampere. So take it to 1000 top side. So this will be IR. Now here we can write also VR is 124 divided by root 3. This is as reference. So it is 71.6 at the angle of kV. So this is phase voltage. Now we are going to with the expression of ABCD parameter. Vs is equal to AVR plus BIR. So Vs is equal to 0.986 at the angle of 0.32 degree into 71.6 angle 0 plus 70.3 at the angle of 69.2 into 279.36 minus 36.86, and for balancing the unit we have to divide by 1000 here, so that we can get in kV. Vs is equal to 87.84 at the angle of 77.12 kV. And similarly we are going to find Is is equal to CVR plus DIR. So to substitute all this value, I am not writing this again. So you will get Is value as 257.78 at the angle of minus 30.86 ampere. So for finding the power at the sending end, you need to find the power factor. So power factor at the sending end will be 7.12 is the, here we can see that 7.12 plus 30.86. How we are getting this? We have seen, we can see that we have found Is as this is reference 0 degree. So Vs is coming here, and this is 7.12 degree, and this Is is here. Is is coming 30.86. So total power factor angle will be 37.98 degree. So sending it power factor will be cos of 37.98 degree 0.788. Therefore it is asking the power factor it is only asking. Now the third part is that efficiency of line or regulation of line. First we'll find the efficiency of line. So D part we are going to calculate first, efficiency. So for efficiency we have to find this PS and PR. So PS and PR, how can we can find PS? We know the things. So applying root 3 into VSLL, root 3 into 125.14, current is 257.78, cos of 37.98. So divide by 1000 so that we can get in megawatt. So we get 53.52 megawatt. And receiving end power, how you can find? Receiving in power factor is given, and this kVA rating is given. So PR is equal to 60 into 0.8, that is 48 megawatt. So just keep wait for 5 minutes. We will complete this. So efficiency will come as PR divided by PS into 100. So PR we have calculated 48. PS is 53.52 megawatt 100%. So it is 89.68%. And now D part is C part is percentage voltage regulation. So percentage voltage regulation, we know that V is divided by A minus VR divided by VR full load into 100. So Vs is 152.14, 0.986, and VR is 124 divided by 124 into 100. That will come as 24.43%. Is there any doubt? You can just read once more so that everything will clear more. Still, if you have in doubt, you can ask in the next class. So today in the session, what things we have completed? We have completed the modeling of short short length transmission line, medium length transmission line, and long length transmission line. In short length transmission line, we neglect the shunt admittance, and that is very easy to find this ABCD parameter of short length transmission line. So and in medium length transmission line, we use the nominal pi circuit model, and in long length transmission line, we have seen there is little bit long derivation, but that is also not that much hard. So and for long length transmission line, we have also find the equivalent pi circuit modeling here also. So in the next class, we will see the surge impedance loading, and I think that is also important. Surge impedance loading, that is most one of the commonly question asked, and power flow through transmission line also we will see. Thank you, Venkat and Anil. If you have
Thank you, sir.
any doubt or any concern, you can ask. Okay, bye, and happy Diwali to all of you.
Same to you, sir.
Thank you.
Thank you, sir.
Yeah.